Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Take a moment now to let the day loosen its grip, to allow your breathing to slow, without effort, without instruction. There is nothing you need to accomplish here, nothing to solve, nothing to hold on to. This is a place for quiet attention and gentle curiosity. Tonight, we will not be moving toward explosions or catastrophe or sudden endings. Instead, we will drift toward objects that are ancient, enduring, and remarkably calm. Far from Earth, beyond familiar stars, there exist remnants of stellar lives that did not vanish, did not disappear into darkness, and did not tear themselves apart. They remain compact, dense, and quietly balanced. These are neutron stars. They are often spoken about in the same breath as black holes, as if they belong to the same category of danger or mystery. But tonight, there is no urgency in understanding them. Neutron stars are not places where matter is lost. They are places where matter holds on. They are the densest stable objects known to exist, forms of matter compressed to an extent that challenges intuition, yet governed by clear and dependable physical laws. There is nothing sudden about them now, nothing explosive in their present state. They rotate, they cool, they age, slowly, patiently. Many of them have existed for millions and even billions of years. They are not moments, they are eras. As you listen, there is no need to visualize violence or collapse or destruction. Instead, imagine endurance. Imagine a quiet balance between opposing tendencies, gravity drawing inward, matter resisting compression. This balance does not flicker, it does not rush, it holds. Neutron stars exist because the universe allows matter to reorganize, rather than vanish. They are what remains when a star has finished shining, yet has not crossed the threshold into absolute collapse. They represent a pause, a limit, a sustained equilibrium. And this equilibrium is not fragile. It is supported by the most fundamental rules of nature, rules that do not tire, rules that do not weaken with time. As we move deeper into this topic, there will be no equations to follow, no numbers to memorize, no urgency to keep up. The ideas will unfold gradually, layer by layer. You may notice your thoughts slowing, spacing themselves out as the scale of time stretches beyond human concern. Neutron stars do not exist on human schedules. Their processes unfold over spans of time so long that impatience simply does not apply. This is science told at the pace of gravity itself, steady, unhurried. You may already feel a subtle shift, a sense that the noise of daily life is becoming less relevant, less immediate. That is natural, because when attention turns toward objects this old, this dense, this quiet, the mind often follows their rhythm. There is no danger here. Despite their extreme nature, neutron stars are not threats waiting to be unleashed. They are finished with drama. What remains is structure, pressure, and balance. They no longer burn fuel. They no longer expand. They simply exist, and in that existence, they reveal something profound about reality itself. They show us that even under conditions far beyond everyday experience, the universe does not abandon its rules. Instead, it leans on them more heavily. Gravity becomes intense but not chaotic. Matter becomes dense but not confused. Time itself bends slightly, yet continues forward. Nothing breaks. As you settle more deeply into rest, you may begin to sense that this journey is not about reaching a destination. It is about remaining with ideas, long enough for them to soften. Neutron stars are often described with words like extreme or exotic or bizarre, but tonight they can be understood differently. They are calm answers to persistent questions. What happens when gravity becomes overwhelming, yet matter refuses to disappear? What form does stability take? When pressure no longer depends on heat or motion, how does nature enforce limits without drama? These are not questions that demand immediate resolution. They are questions that can be held gently, allowed to drift through the mind without effort. As you listen, you may notice that your body feels heavier, more grounded. That sensation mirrors the subject itself. Neutron stars are objects defined by gravity, by weight, by inward pull, and yet they are not collapsing. They persist. This persistence is the quiet theme of tonight's exploration. Not endings, but continuations. Not destruction, but compression. Not chaos, but law. As we move forward, we will slowly trace how ordinary matter, the same matter that forms planets and people and air, can be transformed without vanishing. We will move gently from the familiar to the unfamiliar, from atoms to nuclei to states of matter that exist nowhere else. But there is no need to anticipate. For now, it is enough to rest with the idea that somewhere in the universe, there are stars that ended their burning long ago and yet still remain, quiet, dense, unchanging, holding themselves together against almost unimaginable pressure. As your breathing continues, slow and natural, allow these thoughts to become background like distant starlight. There is nothing you need to remember, only something to rest within, a sense of scale, a sense of calm, and the reassurance that even at the edge of physical possibility, the universe remains orderly, stable, and deeply, deeply quiet. Far out in the galaxy, where the night is not a backdrop, but an ocean of distance, there are stars that live long, steady lives, and there are stars that live faster, with more weight behind every moment. A star, in its simplest description, is a balance. Gravity pulls inward, patiently, constantly, and pressure pushes outward steadily, continuously. For most of a star's life, that outward pressure comes from heat, not a gentle warmth, but the immense thermal energy generated by nuclear fusion. Fusion is not a flame, not burning in air, not consuming oxygen. Fusion is matter changing its identity in the core, light nuclei joining, becoming heavier nuclei, releasing energy as they do. This energy moves outward, through dense layers of plasma, through radiative transport and convection, and eventually leaves as starlight. And as long as that energy continues to flow, the star remains held up, not suspended, not floating, held up by a pressure gradient, a smooth change in pressure from the center outward, a structured resistance to gravity. In a calm way, it is a story of two tendencies that meet in the middle, inward pull and outward support. This is what makes a star feel so stable, so dependable, so ancient, even though, deep within it, the core is always changing. For a star like the sun, the story is slow, a long, quiet burning of hydrogen unfolding over billions of years. But some stars begin with more mass, and with more mass, gravity presses harder from the start. In these heavier stars, the core must respond. To keep balance, the core must run hotter and compress more and fuse more quickly. So their lives can be shorter, not because they are fragile, but because they are intense. They spend their fuel faster, as if gravity demands a higher payment. It can help to imagine gravity here, not as forceful or violent, but as inevitable. It is simply what mass does. It shapes the structure and sets the conditions. A more massive star has a deeper inward pull, so the star must push back more strongly, and to push back, it must produce more pressure, and to produce that pressure, it must generate more energy, and to generate that energy, it must fuse fuel at a higher rate. This is not drama, it is accounting, a quiet cosmic bookkeeping written in pressure and temperature. As time passes, the star's core changes what it is fusing. Hydrogen becomes helium. Then, in more massive stars, helium can become carbon and oxygen. And if the star is massive enough, the core can progress through further stages, each stage requiring higher temperature because heavier nuclei resist merging. Fusion is easiest with the lightest elements and becomes more difficult as nuclei grow larger. So the core must become hotter and denser to keep fusion going. For a while, each stage of fusion provides pressure, each stage holds gravity back, and the star continues, layered, structured, with shells of different fusion processes, each one contributing to the star's support. But this cannot continue forever, not because the star fails, but because nature has a limit. There is a point where fusion no longer provides a gain, a point where fusing heavier elements does not release energy, but instead costs it. At that point, fusion stops being a source of outward pressure, and the star's core, which has always been in a delicate negotiation, finds itself without its main support. This is the quiet turning point. The star does not become dangerous in this description. it becomes inevitable. Gravity has waited patiently for millions of years, sometimes for tens of millions, sometimes longer. And now, with fusion no longer able to pay the pressure bill, gravity begins to win. The core begins to contract, not as an explosion, not as a shock, but as a rapid inward adjustment. The core becomes denser, and as it densifies, the laws of matter shift their emphasis. In everyday life, matter is governed by electromagnetic forces. Atoms keep their structure because of electrons, because electrons occupy quantum states, because like charges repel, and because the rules of quantum mechanics limit how particles can be arranged. That is why normal matter has volume, why it does not collapse into a smaller and smaller space. But in the core of a massive star at the end of fusion, gravity becomes strong enough to overpower the familiar architecture of atoms. The distances inside matter shrink, electron shells are squeezed, atoms cannot keep their comfortable spacing, and in that tightening, a new kind of pressure begins to matter. At first, there is electron degeneracy pressure. This is not thermal pressure, not pressure from heat. It is pressure from quantum rules, from the fact that electrons cannot all occupy the same state. As gravity squeezes them into a smaller volume, they fill up available quantum states like seats in a theater. When the lower states are filled, electrons must occupy higher momentum states, and that creates a resistance, a pressure, even if the temperature drops. This is one reason stellar remnants can be stable even as they cool. But for the most massive stars, even electron degeneracy pressure is not enough. Gravity continues, and the core becomes so dense that electrons are pressed into closer contact with protons. This is where ordinary atomic identity begins to fade. In a normal atom, protons are confined to the nucleus. Electrons form a cloud around, but under intense compression, electrons are forced into the nucleus, or more precisely, they are forced into interactions where a proton and an electron can transform. The language here can be gentle. A proton can capture an electron, and when it does, the proton becomes a neutron. This is not a choice, not a preference. It is a permitted reaction, when the energy conditions and particle densities make it favorable. As the core densifies, more and more of these transformations occur. Protons become neutrons. Electrons are removed from their familiar role. The star's core becomes increasingly neutron-rich. And as this happens, the concept of an atom, as a nucleus with an electron cloud, is no longer the right description. Matter is becoming something closer to nuclear matter, a substance more like an immense nucleus, spread across a region the size of a city. This is one of the most extraordinary transitions in astrophysics, and yet it can be held calmly, because the core is not doing this to be spectacular. It is simply moving towards stability, under the pressure gravity demands. For a moment, it can help to remember the theme. Gravity presses inward, matter responds, by changing what it is. At this stage, the core is collapsing, but collapse here is not annihilation. It is compression, it is reorganization, it is matter finding new ways to exist. If the star were even more massive, compression might continue beyond the neutron star state. But in the neutron star pathway, something stops the collapse, not suddenly, but decisively. The collapse is halted because, as once matter becomes dominated by neutrons, a powerful form of resistance emerges. Neutrons, like electrons, obey quantum rules. They cannot all pile into the same quantum state. They resist being squeezed into identical configurations. As the density rises, neutrons fill available states, and the pressure from that crowding grows. This is neutron degeneracy pressure. But there is another contributor too, the strong nuclear force. At very short distances, the strong force binds nucleons together, holding nuclei stable. But when nucleons are pushed extremely close, the interaction becomes effectively repulsive, a stiffening of matter. So there are multiple layers of resistance, quantum rules, and nuclear interactions, and together they can halt the inward fall. This is the key idea. A neutron star forms when the inward pull of gravity is balanced by the pressure of neutron-rich matter, and that balance can be stable, long-lived, quiet. If you are imagining a dramatic moment, you can let that go. Instead, imagine a sudden quietness after a negotiation ends. Gravity has pressed, matter has transformed, and now a new equilibrium is established. A compact object remains, a neutron star, small, dense, stable. Now it can help to connect this to the contrast you already carry gently. A black hole is defined by a horizon, a boundary beyond which escape is impossible. A neutron star has no such boundary. It is intensely compact, but still a physical surface, still a region from which light can escape. This means neutron stars belong to the realm of observation. They can emit light, heat, radio waves, X-rays. They can be found, timed, studied. They are not hidden in the same way. They are not absent. They remain present. And because they remain present, they become laboratories. Not laboratories made by humans, but laboratories built by nature. Places where the same physics that governs atoms and particles is tested under extreme conditions. In a sleep narration, we can let that feel comforting, because it means the universe is consistent. The same laws that describe the small also describe the immense. When the core becomes a neutron star, it does not keep the old size of the star. The star's outer layers, no longer supported by fusion in the core, can be shed. In some cases, they are expelled into space, but we do not need to focus on that, because the subject of our calm attention is what remains. The compact core, a neutron star's size, is difficult for the mind, because it compresses something star mass into something city scale. You do not need to picture exact dimensions, but it can be restful to hold the contrast softly. A star's mass, in a region that could fit into a small slice of a planet's scale, a tiny cosmic seed of weight. And because it is so compact, gravity at its surface is intense. If you could stand near such a surface, the pull would be enormous, and yet the star would not be pulling you into a horizon. It would be pulling, as any massive object pulls, just far more strongly. The remarkable thing is not that gravity is strong. The remarkable thing is that matter resists it. That matter does not simply yield, that the universe permits stable matter, even at densities where atoms are no longer the right description. This is where neutron stars become almost black holes in the sense of compactness. They are close to the boundary, but they remain on the visible side. They remain matter, in a way black holes do not. So if black holes are often described as places where matter is lost behind a horizon, neutron stars can be described as places where matter holds on at the edge. It is a different kind of story, not disappearance, but persistence. Now it can help to bring in a gentle, careful sense of just how dense this is. In a neutron star, density is so high that familiar comparisons become strained, but a single simple image can be used lightly. Imagine matter packed so tightly that a small amount of it would weigh unimaginably more than the same volume on Earth. You do not need to hold the numbers, just the feeling that the spacing between particles has changed, that empty space inside atoms has been largely removed, that what remains is matter in a compressed nuclear state. This is why neutron stars are sometimes described as gigantic atomic nuclei, not literally, but as a useful intuition, because they are made mostly of neutrons, and because their density approaches that of nuclei. All of this has been achieved not by artificial machinery, but by gravity. Gravity, doing what it does, given enough mass and enough time, and now we can return to the calm aftermath. Once a neutron star forms, it is not burning, it is not generating energy through fusion, it is a remnant, but remnant does not mean lifeless. It is still active in certain ways. It can rotate, often quickly. This rotation is another quiet consequence of collapse. When an object shrinks, its rotation can speed up, the way a skater spins faster when drawing in their arms. A star's core, once large, becomes much smaller, and its angular momentum remains, so the remnant can spin rapidly. Again, no spectacle needed, just steady motion, a small, dense object turning in silence, and through that turning it may produce beams of radiation. If its magnetic axis is not aligned with its rotation axis, the emission can sweep across space, and when those beams cross Earth, we detect pulses. This is how pulsars are found, as clocks, as regular signals. As stability made visible, even the word pulsar can be held gently, not as flashing alarm, but as steady timing. A distant lighthouse in the dark, marking the passage of time with remarkable precision. And then there is cooling. A neutron star begins hot, born from a compressed core. But with time, it cools. It radiates away energy. Not rapidly, over long spans, it becomes, in a sense, a slowly fading ember. But because it is so dense, its internal physics is unusual. Heat transport, particle behavior, and the state of matter all influence how it cools. We will explore those ideas later, slowly. For now, it is enough to say, Neutron stars age, they endure, they persist, they can exist for millions, for billions of years. In the galaxy's long story, neutron stars can outlast the civilizations that study them. They are older than human history, older than written language. Some are older than complex life on Earth. They remain quietly, a stable survivor of compression. Now, one of the most important calm reassurances is to remember that neutron stars are not black holes. They are compact and their gravity is strong, but they have surfaces, they have structure, they emit, they can be observed, and the presence of a surface matters. It means there is a place where matter ends and space begins, a boundary you can approach in thought, not a boundary that erases. This is why neutron stars are such powerful objects for learning. They allow us to study strong gravity without crossing into the realm where information is hidden. They allow us to study dense matter without requiring us to create it artificially. They are nature's own experiments, and they are quiet. Not quiet because nothing happens there, but quiet because what happens according to law, orderly. In the end, the formation of a neutron star can be understood as a sequence of balances. At first, fusion balances gravity. Then, fusion fails to provide enough pressure. Then gravity compresses the core. Then matter changes. Electrons are captured. Protons become neutrons. Atoms cease to be the correct description. And finally, neutron-rich matter provides pressure that balances gravity again. A new equilibrium. A compact star. Stable. If you feel your attention drifting now, you can let it drift. Because the core message is simple. Neutron stars are what happens when gravity nearly wins, but not completely. When matter is pushed to the edge, and still, it holds together. This is not a story of destruction. It is a story of persistence, a story of the universe allowing stability, even under extraordinary conditions. So as you rest, let your mind hold one quiet image, a dense, city-sized remnant, older than almost everything you know, sitting in the dark between stars, not threatening, not rushing, simply existing, balanced, held up by the deepest rules of matter, and by the patient, constant pull of gravity. If you are still awake, let the mind soften a little more. And if you are already drifting, then these ideas can simply pass by, like distant lights seen through half-closed eyes. We are going to stay with something very gentle tonight, even as it reaches into the deepest rules of physics, because there is a kind of strength in the universe that does not come from heat or motion or energy burning away. There is a strength that comes from order, from constraint, from the quiet fact that nature does not allow everything to be placed everywhere. This is where the phrase degenerate matter enters. It sounds severe, but it is not. It is a technical phrase, describing a state of matter where pressure is not primarily created by temperature. Instead, pressure arises because of quantum mechanics, because of how particles must arrange themselves. So when we say degenerate matter, we are not naming a substance like iron, or water, or stone. We are naming a condition, a way matter behaves when it is squeezed so strongly that ordinary descriptions no longer work well. In everyday life, pressure often depends on heat. A hot gas pushes outward because its particles move quickly, they collide, they bounce, and the motion itself creates pressure. If the gas cools, it moves less, and the pressure drops. That is familiar, but there are regimes of nature where cooling does not remove pressure. Because the pressure is not coming from motion, it is coming from the rules that govern what particles are allowed to do. This is one of the most calming and deeply reassuring ideas in physics, that there is a kind of support that remains even when the universe grows cold, a kind of pressure that does not fade just because time passes. To understand this, we can move slowly and keep the images simple. In quantum mechanics, certain particles follow a rule called the Pauli exclusion principle. Electrons do, neutrons do. This rule is quiet and absolute. It says, in essence, you cannot place identical particles in exactly the same state, not in the same quantum state. In a loose, sleep-friendly way, you can imagine a set of available states, like positions and momenta that the universe allows. And these states can be filled. When matter is not very dense, particles have plenty of room. They can occupy low-energy states and spread out comfortably. But when matter is squeezed, the available low-energy states fill up. And once those are full, particles are forced into higher energy states, not because they want to be, but because they must be. This must be is where the pressure comes from, because forcing particles into higher energy configurations costs energy, and nature responds with resistance. That resistance becomes pressure. So degeneracy pressure is not a pressure of heat, it is a pressure of arrangement, a pressure of permitted structure. In a cold gas, the particles can slow down. In degenerate matter, the particles cannot all drop into the lowest possible state. They are prevented by the exclusion principle. So even if you remove heat, the pressure remains. This matters profoundly for stellar remnants, because it means a dense object can cool and still remain supported. A remnant can become cold and quiet and still resist collapse. That is not a small detail. It is a cornerstone of why neutron stars can be stable. Now, let's make one thing especially clear, in a calm way. Classical physics, the physics of everyday intuition, starts to fail when densities become extreme. It is not that classical physics becomes wrong in its domain, it is that it becomes incomplete. At ordinary densities, you can often treat matter as if particles are little objects, with well-defined positions and velocities, moving around, and you can describe pressure as collisions. But when density becomes enormous, the wave nature of particles becomes unavoidable. You can no longer pretend the particles are separate and independent. Their quantum states overlap, their allowed arrangements become constrained, and it is those constraints, not collisions, that dominate the pressure. This is why the interiors of white dwarfs and neutron stars are quantum objects on a macroscopic scale. They are not quantum in a mystical way, they are quantum in the simplest sense. Their stability depends on quantum rules. Now, we can move gradually through the sequence. First, consider electron degeneracy. Electrons are light, and they are abundant in ordinary matter. In a normal star, electrons move freely in a plasma and pressure is mostly thermal. But in a stellar core that is collapsing, as density rises, electrons are packed closer and closer. Their available states fill. They are forced into higher momentum states. That produces electron degeneracy pressure. This is what supports white dwarfs. A white dwarf is a stellar remnant supported primarily by electron degeneracy pressure. It is compact, but not as compact as a neutron star. It is dense, but not at nuclear density. In a white dwarf, atoms have been stripped, electrons are free, but nuclei still exist as nuclei. Matter is compressed, yet still described in a framework where nuclei remain distinct. Electron degeneracy pressure can hold gravity back for a wide range of masses, but it has limits, and for the most massive stellar cores, the inward pull becomes too strong. Then the story changes. When electrons are squeezed into extreme conditions, they can be captured by protons. And as that happens, electrons are removed as the primary support. The matter becomes neutron-rich. And now degeneracy pressure comes from neutrons. Neutron degeneracy. Neutrons are much more massive than electrons, and because they are massive, their behavior under degeneracy has different characteristics. But the essential rule remains: neutrons cannot all occupy the same state. As gravity squeezes them into smaller volumes, they fill states and resist further compression. This resistance becomes neutron degeneracy pressure, and it is one of the key pillars of neutron star stability. Now, it is important to stay gentle here. Degenerate matter is sometimes described as matter that is incompressible. That word can be misleading if taken literally. Neutron star matter can still be compressed. Density still varies with depth. The star still has structure. But in practical terms, as density rises toward nuclear density, matter becomes extraordinarily stiff. It becomes very difficult to compress further. Not impossible, but strongly resisted. It is a bit like trying to compress a spring that has become extremely rigid. Each additional push requires far more force than the last. In a neutron star, gravity provides that force. But even gravity has limits depending on the mass of the star, so degeneracy and nuclear forces together create a kind of pressure profile that can balance gravity. This is the essence. A neutron star is stable because quantum rules and the strong nuclear interaction produce pressure that does not depend on heat. So the star can cool, it can become quieter, it can age, and still hold itself up. That is one of the most soothing truths in this subject. Now, we can return to the difference between thermal pressure and degeneracy pressure, and let it become a calm anchor. Thermal pressure depends on temperature. Degeneracy pressure depends on density, on how tightly the particles are packed. In thermal pressure, cooling weakens support. In degeneracy pressure, cooling does not remove the fundamental resistance. In fact, in some cases, cooling can even make the degenerate description more accurate because thermal agitation becomes less important. So in a way, degenerate matter is naturally suited to the long, quiet future of the universe. It is pressure that persists, even in coldness. Now, there is an even deeper reflection that fits perfectly with the sleep-like pace. Degeneracy pressure is a kind of stillness turned into strength. It is not motion pushing outward, it is a limit on arrangement, a law that says there is only so much togetherness allowed, and that law produces macroscopic consequences. A star can become an object the size of a city and remain stable, because particles cannot all fall into the same state. You can let that idea settle. Matter is stable, not only because of forces, but because of rules. And those rules are quiet. They do not announce themselves. They do not change with mood or time. They hold. Now, let's gently revisit something you may have heard before. In everyday materials, we talk about hardness, rigidity, strength. But those are emergent properties, coming from chemistry and structure. In neutron stars, strength comes from something more fundamental, from quantum statistics, from the exclusion principle, from the deep architecture of the universe. And this is why the subject can feel like matter at the edge of reality, because it is not just a star, it is a physical regime, a place where the universe says, here is how matter behaves, when there is almost no empty space left. Here is how stability works. When heat is not the main support, here is what becomes important, when density dominates everything. Now, it is also important to connect this to why classical physics fails here. In classical thinking, you might imagine compression as simply pushing particles closer and closer, but quantum mechanics adds a new layer. As you compress particles, you are not only changing distances, you are changing allowed states. You are filling a state space. And when that fills, pressure rises. So the pressure is not just a mechanical response, it is a quantum response. This is why a neutron star is, in a meaningful sense, a macroscopic quantum object. Not because it is mysterious, but because its stability comes from quantum principles. Now let's connect the white dwarf versus neutron star difference in a slow, calm way. A white dwarf is held up by electron degeneracy. A neutron star is held up by neutron degeneracy and by nuclear interactions. The difference arises because the path of compression changes the composition of matter. If electron degeneracy could hold indefinitely, the core would remain in a white dwarf-like state. But beyond a certain mass and density, electrons are captured, protons become neutrons, and the matter changes. So the support mechanism shifts. The universe transitions to a new kind of stable remnant. This is not a failure, it is a natural reconfiguration, a new equilibrium made possible by deeper rules. Now you might wonder, in a distant, sleepy way, if degeneracy pressure is so powerful, why does anything ever collapse further? Why are there black holes at all? And the answer is gentle, because degeneracy pressure has limits. Not because the rules break, but because gravity can become strong enough when there is enough mass that no stable arrangement exists that can resist it. At that point, the path leads beyond. But for neutron stars, we are staying on the stable side. We are staying in the regime where matter can still resist, where pressure can still balance gravity, where the universe still permits a surface, a structure, a star-like object. And that is the calm boundary we are exploring. Now, one last gentle clarification about the phrase degenerate itself. In everyday language, it can sound negative, but in physics, it is neutral. It simply means that the particles occupy the lowest available energy states, up to a maximum set by density. It means the matter is governed by quantum statistics. It means the pressure is not thermal. So when you hear degenerate matter, you can let it mean matter supported by quantum rules, matter that remains strong, even as it grows cold. Now, if you have been listening quietly, you may notice a strange comfort in all this. The idea that the universe contains forms of stability that do not depend on burning, that do not depend on constant activity, that do not require constant replenishment. Neutron stars, once formed, can persist. Because the stability is structural, written into the rules, it is as if the universe has a deeper layer of support, reserved for extreme conditions. And that layer holds. So as you rest, let the central idea of this section become a soft refrain. Degenerate matter is not a material, it is a state where pressure comes from arrangement, not temperature, a state where quantum rules prevent unlimited compression, a state where cooling does not remove support, a state that allows a neutron star to remain quiet and stable on timescales that make the mind slow down. And if your thoughts drift away now, that is perfectly fine, because the universe will keep holding these rules, whether we are paying attention or not. Particles will keep obeying their constraints, matter will keep resisting compression, and somewhere in the dark, a neutron star will keep existing. Not burning, not exploding, not changing quickly, just holding on. If you are comfortable, let your attention drift inward a little more, not toward effort, but toward a quieter kind of clarity, because now we can do something gentle. We can imagine descending, not through a cavern, not through rock and fire, but through layers of matter, organized by pressure. A neutron star is small in radius, but immense in depth of physics, and the deeper you go, the more the familiar idea of material dissolves, not into chaos, but into new kinds of order. So let the image be simple, a surface, a thin outer layer, then deeper layers, each one defined by what pressure allows and what density demands. And as we go, we will keep reminding ourselves, this is not a place of sudden transitions. The changes are gradual. A neutron star is a gradient, a smooth increase in density with depth, a smooth shift in what matter can be. To begin, there is the surface, the outermost boundary, where the star meets space. This surface is not like the surface of a planet. It is not an ocean, not air, not soil. It is an extreme solid, a crust, formed under immense gravity. If you could approach it in thought, you would find that gravity holds everything tightly. The atmosphere, if present at all, is thin, and beneath it, matter is compressed into heavy nuclei. The star's outer crust can be imagined as a lattice, a crystalline arrangement, not crystals like salt, but a crystal made of atomic nuclei. Imagine a structure where the nodes of the lattice are nuclei heavier than those we find commonly on Earth, and between those nuclei, electrons move freely. Because at these densities, electrons are not bound in familiar atomic shells, they form what physicists call a degenerate electron gas. Again, no need to hold the term, just the idea. Electrons are present, but not attached to individual atoms. They are shared, spread through the lattice. This combination, a lattice of nuclei and a sea of electrons, creates a rigid crust. It is matter organized by pressure. Now, one of the most sleep-friendly truths about a neutron star is that the star is stable because of pressure gradients. The deeper you go, the higher the pressure, and matter responds by changing its structure. So as we descend, density increases, the nuclei in the crust become more neutron-rich, because as pressure rises, it becomes favorable for matter to pack in neutrons. Neutrons do not carry electric charge, so they can accumulate in nuclei without increasing electrostatic repulsion in the same way protons do. As you go deeper, nuclei become increasingly heavy and neutron-rich. But nature has another threshold. At some depth, the nuclei can no longer hold on to all their neutrons. The environment becomes so dense that neutrons begin to drip out. This is called neutron drip. Not a dramatic drip, just a technical phrase. It means free neutrons appear outside nuclei. So now the crust becomes a mixture, a lattice of nuclei, electrons moving through and free neutrons seeping between. This region is often called the inner crust, and here, matter becomes stranger, but still orderly. The free neutrons are not simply particles bouncing around like a normal gas. At these densities, and at the temperatures of an old neutron star, the neutrons can behave collectively. They can form a superfluid. A superfluid is a state of matter where flow can occur with extremely low internal friction. Again, this is not magical. It is a quantum collective phenomenon. The neutrons behave as a coordinated system, so in the inner crust you can imagine something very unusual. A rigid lattice, embedded in a sea of degenerate electrons, while free neutrons flow through the spaces, not turbulent, not chaotic, a quiet quantum fluid, moving through the crystal-like structure. This is one of the places where neutron stars feel like matter at the edge of reality. Because it is difficult to find an Earth analogy, we do not have everyday objects that combine a crystalline lattice with a superfluid component under extreme gravity, but the neutron star holds it steadily. Now, as we continue deeper, The density keeps rising, the spacing between nuclei shrinks, the distinction between nuclei and the surrounding medium begins to blur, and here physics suggests the possibility of unusual nuclear shapes. In some models, nuclei may not remain roughly spherical. They may stretch into rods, or flatten into slabs, or form complex geometries, because matter is trying to minimize energy under competing forces. The strong nuclear force tries to bind nucleons, the electromagnetic force creates repulsion among protons, and the pressure of the environment compresses everything. The result can be structured complexity. Sometimes this is called nuclear pasta. Again, it is just a nickname. It refers to shapes that resemble sheets or strands in mathematical models. But the deeper truth is calm. Even here, matter finds patterns. Even here, matter does not become random. It becomes structured. Because structure is what minimizes energy in extreme conditions. So we can hold the image gently, not as spaghetti or playful shapes, but as matter becoming geometrical, finding the most stable arrangement under enormous compression. Now we approach the boundary between crust and core. At some depth, the lattice structure may dissolve. The idea of distinct nuclei embedded in a medium becomes less useful, and we enter a region where matter becomes more uniform. This is the outer core. Here, matter is dominated by neutrons, but it is not only neutrons. A small fraction of protons remains, and electrons remain, to keep overall charge balance. In some conditions, muons may appear as well. Muons are particles like heavy electrons. They can appear when the density is high enough that it becomes energetically favorable for them to exist. You do not need to remember that, only the theme. As density rises, the composition adjusts. Particles appear or vanish, depending on what minimizes energy. The neutron star is always seeking the lowest energy configuration, given its constraints, and the constraints are immense. In the outer core, neutrons may again form a superfluid, and protons may form a superconducting component. Superconductivity, like superfluidity, is a collective quantum state. It means electric currents can persist with very low resistance. So in the core, you may have a remarkable quietness. Superfluid neutrons and superconducting protons, a macroscopic quantum system, stable. This matters for how neutron stars rotate, for how they change their spin over time, and for how magnetic fields are anchored and evolve. But we will keep the feeling calm, because the key point is this: a neutron star is not just dense, it is organized, it has layers, and each layer is defined by a particular balance of forces and quantum rules. Now we move toward the most uncertain region. The inner core, here, densities may become several times nuclear density. And this is where our knowledge becomes less certain, not because physics fails, but because we cannot yet constrain the exact equation of state. The equation of state is the relationship between pressure and density and composition. Under these conditions, it is the rule book that tells you, if the density is this, then the pressure is that. And that rule book depends on what matter is made of. At the highest densities, matter may remain mostly neutrons. Or it may begin to include other particles. One possibility is that hyperons appear. Hyperons are particles that contain strange quarks, heavier relatives of neutrons and protons. In ordinary conditions, hyperons are unstable, but in a neutron star core, the extreme density can make their presence energetically favorable. Another possibility is that quarks become less confined, that the boundary between individual neutrons and protons and a more free quark matter begins to blur. In that scenario, the core might contain a form of quark matter or a mixed phase. These are not confirmed, they are possibilities. And this uncertainty is not unsettling. It is one of the quiet frontiers of modern astrophysics. Neutron stars are among the few places in the universe where nature might reveal these exotic phases. And yet, even without knowing the exact details, we know something important. We know that whatever the core contains, it must produce enough pressure to support the star, or else the star would not exist in that stable form. So the existence of neutron stars and the measured masses of the heaviest ones already constrain what the equation of state can be. This is one of the elegant parts of the story. Observation guides theory. The sky tells us what matter can do. Now let's return to the idea of gradual transitions. The neutron star is not a set of hard boundaries. It is a continuum. Density increases smoothly with depth. Composition changes gradually. The star is a layered response to pressure. That is why it can be helpful to imagine the neutron star as a kind of interior landscape, not a chaotic one, but a calm gradient. At the surface, a rigid lattice of heavy nuclei. Deeper, free neutrons begin to appear. Deeper still, a mixture becomes more uniform. Then, a core dominated by neutrons, possibly superfluid, and deeper still, a region where the true state of matter is uncertain, but certainly extreme. This is the layer-by-layer approach. We do not need to force it. We can let it settle as a slow descent. Now, there is another layer of calm to add, the strong nuclear force. In ordinary matter, the strong force is something we rarely consider. It binds nuclei. It holds protons and neutrons together in atomic nuclei. But in a neutron star, the strong force becomes a major player. Because the distances between nucleons become so small that nuclear interactions shape the stiffness of matter, the strong force is attractive at certain ranges. It binds, but at extremely short ranges, the effective interaction becomes repulsive. This repulsion is part of what prevents matter from collapsing indefinitely. So in a neutron star, the resistance to compression is not only degeneracy pressure, it is also nuclear interaction. This is why the neutron star's equation of state is complex. It is not just a simple quantum packing problem, it is also a many-body nuclear problem. How do neutrons and protons interact when packed densely? How does the presence of a small fraction of protons affect things? How do possible hyperons or quark matter change the stiffness? These are deep questions, and the universe holds the answers inside these compact stars. Now, we can let this become peaceful, because uncertainty in science is not a failure. It is an honest boundary. It tells us where we are still learning, and neutron stars, quietly rotating in the dark, are teaching us. Even when we do not yet have complete certainty, this is the calm frontier, not a cliff, a shoreline, where knowledge meets the unknown. Now, one more gentle image. Think of the neutron star interior like geology, not because the materials are similar, but because the idea of layers is similar. In geology, layers form under pressure and time. In neutron stars, layers form under pressure and fundamental physics. And just as Earth's interior is not directly accessible, yet can be studied through waves and measurements, the neutron star's interior is studied indirectly, through mass and radius constraints, through pulsations, through cooling curves, through gravitational waves from neutron star mergers, through timing, through spectra. We learn about interior structure by reading the star's external behavior, and that is why the interior is such a powerful topic. Because it links the smallest physics to the largest observations, the behavior of neutrons, and the behavior of stars, in one object. Now let the main ideas of this section settle. A neutron star has an outer crust, a lattice of heavy nuclei and a sea of electrons. Deeper, neutrons begin to drip free, forming an inner crust with free neutrons, possibly superfluid. Deeper still, the core becomes more uniform, dominated by neutrons with a small fraction of protons and electrons. And deepest, the inner core remains uncertain, with possible exotic states, hyperons, quark matter, or other phases. Throughout, the strong force matters and quantum rules matter. And the changes are gradual, layer by layer, not sudden, not violent, just the universe adapting to pressure. As you rest, you can let a final quiet image remain, a small, dense star, with an interior that is not a simple ball of matter, but a carefully layered structure, a gradient of density, a gradient of physics, a hidden world, held steady by laws that do not need your attention to keep working. And if sleep comes now, it can come gently, because even in the densest places known, there is still structure, still order, still a calmness, deep within gravity's grip. If you are still listening, let the mind become even quieter, because now we are going to speak about gravity, not as a push or a pull, but as a shape, a way the universe arranges distance and time. A neutron star is small, dense, and compact. And compactness has a simple meaning. It means a lot of mass in a small region. When mass is concentrated like this, gravity becomes strong. But strong gravity does not have to feel frightening. It can be understood as geometry, as curvature. In general relativity, mass and energy influence the shape of spacetime, and spacetime, in turn, guides the motion of matter and light. This can be held as a gentle picture, not as bending in a visible way, but as a quiet change in what straight means. A straight line in curved spacetime is not the same as a straight line on a flat surface. Light still travels along the straightest possible path, but that path can curve, because the space it travels through is curved. So near a neutron star, light does not behave exactly as it would far away. Its path can be deflected, its energy can be shifted, its timing can change. These are not dramatic claims, they are subtle and measurable. They are the calm signatures of strong gravity. Now, one of the most soothing ways to approach relativity is to remember that it does not describe gravity as a force, not in the same sense as a rope pulling you. Instead, it describes gravity as the structure of space-time, and a neutron star is one of the places where that structure becomes intense. The star is compact enough that the curvature near its surface is significant. Space is not flat there. Time is not the same there, and yet the world remains consistent, because relativity is a rule, not a surprise. Now, let's begin with something simple. Time dilation. Time dilation means that time passes at different rates, depending on gravitational potential. Near a very massive object, clocks run more slowly, compared with clocks far away. This is not a poetic statement. It is a real physical effect. Near a neutron star, time is slightly slower. If you could place a clock on the surface and compare it to a clock far from the star, the surface clock would tick more slowly, not because it is broken, but because time itself, as measured by that clock, is part of the curved space-time environment. This is one way to sense, without fear, that neutron stars are close to the boundary of black holes. Because black holes represent an extreme case, at an event horizon, the gravitational effects become so strong that escape is no longer possible. But neutron stars are not at that limit. They are close enough to show strong relativistic effects, yet not so far that the universe becomes sealed. This difference matters, because the absence of an event horizon means light can still climb away, signals can still reach the wider cosmos, so the neutron star remains a communicator, a visible object. Now, consider gravitational redshift. Light leaving a gravitational field loses energy. This is another way of saying, as light climbs out, its wavelength is stretched. It shifts toward the red end of the spectrum. Near a neutron star, this redshift can be significant. Photons emitted from near the surface arrive to distant observers with slightly reduced energy. Again, no need for numbers, just the gentle logic. Climbing out of a deep gravitational well costs energy. The photon pays that cost, not by slowing down, but by changing frequency. So when we observe radiation from neutron stars, we must remember the star's gravity has modified the light. The light carries a signature of the space-time curvature it escaped from. Now, we can speak softly about escape velocity. Escape velocity is the speed needed to leave the gravitational influence of an object without falling back. For a small planet, escape velocity is modest. For a star, it is larger. For a neutron star, it becomes a substantial fraction of the speed of light. This is another reason neutron stars are described as almost black holes. Because for a black hole, the escape velocity at the event horizon is equal to the speed of light. At that boundary, escape is impossible, but for a neutron star, the escape velocity is high, yet still below the speed of light, so light can still leave. It is difficult in the sense that the gravitational well is deep, but it is possible, and that is the key distinction. No horizon, no one-way boundary, just intense curvature. Now there are other orbital effects near neutron stars. If matter orbits a neutron star, it experiences strong gravitational fields. Orbits can be fast, close in, and general relativity predicts subtle phenomena, such as precession. Precession is the slow rotation of an orbital ellipse. An orbit is not a perfectly closed loop, as it would be in idealized Newtonian gravity. Instead, the orbit's closest point shifts gradually. The path slowly turns. This is another gentle sign that space-time is curved. This effect was measured around the Sun, in the motion of Mercury, but around neutron stars the effect can be far stronger. And this matters for binary systems. When a neutron star orbits another star or another neutron star, their interaction can reveal relativistic gravity. Timing, orbital decay, and other signals can be used to test general relativity. Once again, we do not need the technical machinery here, only the calm concept. Neutron stars let us study gravity, in a regime where relativity is not a small correction. It is a major influence. Now, it can be tempting to compare neutron stars and black holes too directly, but a calm comparison is helpful. A black hole is defined by the presence of an event horizon. A neutron star is defined by the presence of a surface. That difference changes everything. A surface means matter is still present in a star-like form. It means there is a boundary where physics of matter matters. It means radiation can be emitted from a physical layer. It means there can be hotspots, magnetic polar regions, and emission mechanisms tied to a solid crust. A black hole does not have that kind of surface. So neutron stars allow us to connect two realms, the realm of strong gravity and the realm of matter. They show us that strong gravity does not automatically erase matter. It reshapes its environment, but matter can still persist. Now, there is another calm way to describe why neutron stars are not black holes. It is about radius. For any given mass, there is a characteristic radius called the Schwarzschild radius. If an object of that mass is compressed inside that radius, an event horizon forms. That is the black hole condition. A neutron star has a radius larger than the Schwarzschild radius for its mass. It is close in a certain sense, but not inside, so it remains a star-like object. It remains in the visible universe. This is what it means to have strong gravity without an event horizon. The star bends space and time, but does not trap light completely. It slows time, but does not stop the cosmos from receiving signals. It redshifts light, but does not prevent emission. This is a boundary state, a near limit. And that is why neutron stars are so valuable, because we can observe them, we can test physics with them, we can learn about the interaction between gravity and matter. Now there is a quiet philosophical undercurrent here that remains mostly scientific. Gravity is geometry. Mass tells space-time how to curve. Space-time tells matter how to move. This is not metaphor. It is a concise description of the theory. And in neutron stars, you see it clearly, because matter is dense and gravity is strong, and the effects are not hidden. So near a neutron star, the concept of time becomes more local. It depends on where you are, and the concept of energy becomes more relational. Light changes as it climbs. Everything becomes interconnected, not in a mystical sense, but in a precise physical sense. The structure of the universe becomes visible. Now, it is also important to remember, relativity does not make the neutron star unstable by itself. Strong gravity does not imply collapse. Collapse happens if there is not enough pressure support, but if the equation of state of the matter provides enough pressure, the star can remain stable. So strong gravity and stability can coexist. That coexistence is part of tonight's calm theme. The edge of possibility, without crossing into breakdown. Now there is one more subtlety that is worth holding gently. When gravity is strong, it affects what you can see of the star. Light paths bend. This means that an observer far away can sometimes see more of the star's surface than simple geometry would suggest, because light emitted from regions near the far side can be bent toward the observer, so the star's surface can appear, in a sense, more visible than expected. Again, not in a dramatic way, just in the quiet way that curvature influences sightlines. And this bending of light is one more reminder. Space near a neutron star is not flat. Now, as we let these ideas settle, we can summarize the calm pillars. A neutron star is compact enough that general relativity matters strongly near its surface. Time runs more slowly near it. Light is redshifted as it escapes. Escape velocity is high, yet still below the speed of light. Light paths bend and orbits can precess, but there is no event horizon. The star has a surface. Signals can escape. Information remains connected to the rest of the universe. So neutron stars occupy a special place. They let us study strong gravity without losing access. They are near the boundary, but not across it, and that makes them quietly profound. Now, if you are becoming sleepier, let that be the natural outcome. Because the physics here, while deep, is also steady. Relativity does not shout, it does not add chaos, it simply describes what is. A universe where mass shapes geometry and geometry shapes motion. A universe where time is not absolute but consistent. A universe where light carries the imprint of gravity as it travels. And somewhere, in the dark between stars, a neutron star continues to exist, holding matter together, bending space gently around it, slowing time slightly at its surface, letting light escape, letting the cosmos know that even at the edge of extreme gravity, reality remains lawful, stable, and quietly, beautifully, calm. If you are still awake, let your breathing remain soft, and if you are drifting, then these ideas can simply float past, like distant stars, seen without effort. Now we turn toward one of the most distinctive qualities a neutron star can carry: magnetism. Not the magnetism of a small object on a desk, not the faint pull of a refrigerator magnet, but magnetism as a large-scale feature of a compact star, a field threaded through space, anchored in dense matter and sustained over long spans of time. Some neutron stars have magnetic fields that are strong, others have magnetic fields that are extraordinary, and the neutron stars with the most extreme magnetic fields are called magnetars. The word can sound dramatic, but the reality, as always, is lawful. A magnetar is not a creature of violence. It is a neutron star, defined by a particular physical parameter, a magnetic field of immense strength. And a magnetic field is not a mystery substance. It is a structure, a configuration of electromagnetic influence, a way charged particles and currents shape their surroundings. In everyday life, magnetic fields arise from moving charges and from the intrinsic magnetic properties of particles. In stars, magnetic fields can be generated and maintained by plasma motions and rotation and large-scale currents. But a neutron star is not an ordinary star. Its matter is dense, its crust is solid, its interior may be superconducting, and its rotation can be rapid. These conditions change how magnetic fields behave. Now, the first gentle idea to hold: a neutron star inherits magnetism. A star that becomes a neutron star already had a magnetic field. Not necessarily a magnetar-level field, but some field. And when a star collapses to a much smaller radius, the magnetic field can become far stronger, simply because of compression. This is a quiet conservation principle. If you take magnetic flux and you compress the area through which it passes, the field strength increases. It is not a choice, it is geometry. So one reason neutron stars can have strong magnetic fields is simply that the star's core shrinks dramatically. A large magnetic structure is squeezed into a much smaller volume, and the field intensifies. But this alone does not always explain magnetars. Magnetars appear to involve additional amplification, something that boosts the field beyond the already strong neutron star range. One likely contributor is rapid rotation at birth. When a neutron star forms, it can begin life spinning very quickly, and rapid rotation can drive fluid motions in the newborn star. Those motions can act like a dynamo, a process that converts rotational and fluid energy into magnetic field energy. Again, no need to picture turbulence. Just the concept: a rapidly rotating newborn neutron star with conductive matter can amplify magnetic fields. So magnetars may be born when conditions align, a core collapse that leaves behind a neutron star with rapid rotation and the right internal conditions to strengthen its field enormously. Now let's hold another calm point. Magnetism does not only exist inside the star. A magnetic field extends outward. It threads the space around the star. The region dominated by a neutron star's magnetic field is called its magnetosphere. The magnetosphere is not a rigid shell. It is a space where charged particles and electromagnetic fields interact strongly. In the magnetosphere, electrons and other particles can be guided along magnetic field lines. They can be accelerated. They can emit radiation. This is how many neutron stars become visible. They are compact, but their fields reach outward, influencing a larger region of space. Now, magnetars are particularly notable because their magnetic fields are so intense. And when a magnetic field is extremely strong, it can do more than guide particles. It can stress the star itself. A neutron star has a crust, a rigid outer layer, and if the magnetic field changes over time, or if it is twisted, or if it shifts its configuration, it can exert stress on that crust. Imagine the crust as a solid lattice, and the magnetic field as a set of invisible lines under tension. In most contexts, magnetic fields pass through matter without mechanical consequence. But in magnetars, the field is so strong that its energy is comparable to the mechanical strength of the crust. So the field can deform the crust slightly. It can load it with stress. Over time, the crust may adjust, it may crack or shift, not as an explosion, but as a sudden release of built-up strain. This is sometimes described as a starquake, a quiet term. A starquake is not like a planet's earthquake in every detail, but the analogy is gentle enough, a rigid crust under stress rearranging itself. And when the crust rearranges, the magnetosphere can respond. Field lines can reconfigure, particles can be accelerated, radiation can be emitted. This is one reason magnetars can produce bursts of high-energy radiation. But we do not need to dwell on bursts. We can interpret them as signals, as the star's magnetic field shifting toward a lower energy configuration. The star is not acting out. It is relaxing. It is seeking stability, because physical systems tend to move toward lower energy states, and magnetars, with their immense field energy, have more energy available to be released through gradual rearrangement. Now, let's keep the tone calm and analytical. A magnetar's magnetic field is thought to decay over time, not vanish, but slowly weaken. As currents change, as the field diffuses through the crust, as the interior evolves, this decay can provide a source of energy. A magnetar can emit X-rays, not mainly because it is still cooling, but because magnetic field energy is being converted into heat and radiation. This is a subtle and beautiful mechanism. The star is powered, not by fusion, not by accretion necessarily, but by magnetic energy. In other words, a magnetar is a neutron star whose field carries enough energy to influence its thermal and radiative evolution. Now, one question that fits nicely into a sleep narration: why are magnetars rare? The galaxy likely contains many neutron stars. But magnetars are a small subset. This suggests that the magnetar birth conditions are special. Perhaps they require rapid initial spin. Perhaps they require certain progenitor properties. Perhaps they require specific internal instabilities. The precise details are still studied, but the main point is calm. Magnetars are not the default outcome. They are a special case. A neutron star born with an unusually strong field that remains strong enough to shape its behavior for a long time. Now, there is another gentle piece of magnetar physics. Magnetism affects the space around the star. When fields are extremely strong, they can influence the propagation of radiation. They can change how charged particles move. They can create regions where pair production can occur, where photons produce particle pairs in extreme conditions. We do not need to focus on technicalities, only the calm implication. In magnetars, the surrounding environment is deeply electromagnetic. Space near the star is not empty. It is structured by field lines and by particles guided along them. This is why magnetars are important astrophysical objects. They show us what happens when gravity and magnetism both reach extremes. A neutron star is already a strong gravity object. A magnetar adds strong magnetism. So magnetars become laboratories, not only for dense matter, but for electrodynamics in extreme regimes. Now we can tie magnetars gently back to the core theme. Even here, in one of the most extreme magnetic environments known, the story is still about balance. Field energy and matter rigidity, stress and release, structure and reconfiguration. Magnetars are not chaos. They are the universe adjusting. Now, one more calm question. What do magnetars do for astronomy? They provide signals. They emit X-rays. They emit bursts sometimes. They slow their rotation in characteristic ways. They can be detected and studied, and by studying them, we learn about the interior, because magnetic field evolution depends on the crust and core properties, conductivity, superconductivity, crustal composition. So magnetars link the outer observable behavior to the deep internal physics. In a sense, a magnetar's magnetic field is a messenger. It carries information about what the star is made of and how it is structured. Now let's gather the key ideas of this section and let them settle like a quiet summary. A neutron star can have a magnetic field. That field can be intensified during collapse because compression strengthens it. Some newborn neutron stars may amplify their fields further through rapid rotation and internal dynamo processes. When the field is extremely strong, the neutron star is called a magnetar. In a magnetar, magnetic energy can stress the crust. Over time, the crust may adjust. The magnetosphere may reconfigure, and energy can be emitted as radiation, not as a story of danger, but as a system relaxing. Magnetars are rare because the birth conditions are special. They matter to science because they show how matter and fields behave under extreme conditions, and even in these extremes, the universe remains lawful. Now, let the mind rest with one simple image: a small, dense star, turning quietly, its magnetic field extending outward, threading space like invisible geometry. Not a weapon, not a threat, just structure, a pattern in the cosmos, a reminder that even when magnetism becomes immense, it still belongs to the same calm physics that governs a compass needle and a moving charge and the quiet laws of electromagnetism. And if sleep comes now, it can come gently, because the magnetar, for all its extremity, is still at its core, a stable star, held together, obeying rules, enduring in the long quiet dark. If your thoughts are slowing, let them slow. If your breathing is deepening, let it deepen. Because now we can rest in one of the most peaceful ideas in astrophysics, that nature has boundaries. Not harsh walls, not sudden endings, but limits that emerge from the way matter and gravity balance each other. A neutron star is one of those limits. It is a stable answer to a question gravity keeps asking: how compact can matter become and still remain matter? How much mass can be held up by pressure? How close can a star-like object come to the threshold of no return and still remain visible? Neutron stars occupy that region. They are not the final possible outcome, but they are among the final stable ones. And this is what makes them feel like matter at the edge of reality. Because they live close to a boundary where the universe changes its behavior, not by breaking rules, but by enforcing them. Now, the first calm idea to hold. There is a maximum mass for neutron stars, not a perfectly sharp number we know with total certainty, but a real upper limit set by physics. A neutron star is supported by pressure, neutron degeneracy pressure, and the strong nuclear force, and the detailed behavior of dense matter. But as you add more mass, gravity grows stronger, it compresses the star further, it increases the central density, and the pressure must rise to keep balance. At some point, no known pressure support can hold the star up, not because the star fails, but because the equations describing matter, the equation of state, cannot provide a stable solution beyond a certain mass. This is the quiet meaning of the neutron star maximum mass, a limit born from balance. Now, physicists often speak of this with a formal name, the Tolman-Oppenheimer-Volkoff limit. You do not need to remember the name, only what it represents. It is the theoretical maximum mass a neutron star can have before gravitational collapse becomes inevitable. This limit depends on the equation of state, on how stiff matter is, on what particles appear in the core, on how pressure rises with density. If dense matter is very stiff, pressure rises rapidly as density increases. Then a neutron star can hold more mass. If dense matter is softer, pressure rises less rapidly, then the maximum mass is lower. So the exact limit is connected to unknown interior physics. And this is one of the most elegant links in the story. To know the maximum neutron star mass is to learn about matter itself. Now another calm idea. In reality, we do not need perfect theory first. We have observations. We observe neutron stars in binary systems. We can measure their masses, and when we find neutron stars with very high measured masses, we learn something immediately. Matter must be stiff enough to support them. Certain equations of state become impossible, so the sky quietly constrains nuclear physics. This is one of the most satisfying feedback loops in science. Observation shaping theory, and theory guiding what we look for next. Now, if a neutron star exceeds its stability limit, what happens? Again, we do not need drama. We can describe it as a transition. If gravity becomes too strong, pressure support can no longer balance it. The star cannot remain in that stable configuration, and the collapse continues, not to nothingness, but to a different gravitational state, a black hole, a region with an event horizon, a region where the collapse crosses the boundary, and the structure that once existed is no longer visible in the same way. So neutron stars represent the last stable step before that transition. They are the final visible compression of star mass matter before horizons appear. Now there is a gentle nuance. Neutron stars may not collapse only because they are born too massive. They can also gain mass. If a neutron star is in a binary system, it may accrete matter from a companion. Slowly, over long time, adding mass increases gravity, and over time, this can push the star toward its limit. In this case, collapse is not a sudden surprise. It is the long, steady accumulation of mass and then the crossing of a threshold, a quiet boundary. Now, another essential idea. The maximum mass is not just about how heavy. It is also about radius and compactness. A neutron star's mass and radius are tied together. More mass tends to compress the star more, but the exact relationship depends on the equation of state. So when we measure neutron star radii, or constrain them through observation, we learn about the stiffness of matter. A stiffer equation of state tends to produce larger radii for a given mass. A softer equation of state tends to produce smaller radii, so mass and radius together are like a fingerprint of dense matter physics. Now, let's rest with that, because it means neutron stars teach us something rare. They connect two scales, the subatomic scale, where neutrons and protons interact, and the astronomical scale, where stars and gravity shape the galaxy. In a neutron star, nuclear physics is not hidden in a laboratory. It is written into a star's structure, and that structure is tested by gravity. Now we can gently bring in another concept, thresholds rather than absolutes. In physics, it is tempting to imagine neat boundaries, but nature often gives us ranges. It gives us uncertainties. It gives us transitions that depend on details. The neutron star maximum mass is like that. It depends on composition, on temperature, on rotation, on magnetic fields. Rotation, in particular, matters. A rapidly rotating neutron star experiences centrifugal support. Rotation provides an additional outward tendency, not a pressure in the same sense, but a support against gravity. So a rapidly spinning neutron star might be able to support slightly more mass than an otherwise identical non-rotating star. As it slows down over time, it can lose that extra support. This introduces a subtle possibility. A star that is stable while spinning rapidly may become unstable later. As it spins down, again, no need for drama, just the idea of slow evolution, a system drifting toward a threshold. Now, magnetic fields can also play a role. For most neutron stars, magnetic fields do not significantly affect the global stability. But in magnetars, fields are intense. They can influence the star's crust and possibly contribute in subtle ways to structure. But the dominant balance for the maximum mass remains gravity and the equation of state, the deep behavior of dense matter. Now, there is another peaceful angle. Why are these limits important? Because they define what matter can do. They define the boundary between two regimes, stable compressed matter and horizon-forming collapse. So neutron stars are like signposts. They mark a region of physical possibility. They say, here is a configuration nature allows. Here is how far compression can go before visibility ends. And because neutron stars exist in many environments and come in a variety of masses, they help us map that boundary. Now we can speak gently about what they teach us. Neutron stars teach us about the strong nuclear force, because the strong force shapes the stiffness of matter at high density. They teach us about quantum statistics, because degeneracy pressure is essential for support. They teach us about particle physics, because exotic particles may appear in their cores, hyperons perhaps, or transitions to quark matter. And they teach us about gravity, because their compactness makes relativity important. All of these teachings are quiet. Because neutron stars are quiet, they are slow objects. They do not rearrange quickly. They do not change in minutes. They evolve over long time, and their stability is a kind of long-term statement, a continuing proof that a certain equation of state must be possible. Now, observational constraints. This matters because we do not see inside neutron stars directly. We infer, we measure masses, we constrain radii, we observe gravitational waves from merging neutron stars. We study cooling, we study pulsar timing. Each of these provides constraints, and those constraints narrow what is possible inside. The beautiful thing about constraints is that they are gentle. They do not require certainty all at once. They gradually shape our understanding. They carve away what cannot be, leaving what remains plausible. So the study of neutron stars is like slow sculpting, a patient refinement. Now, in the context of this sleep journey, we can hold the most restful conclusion of this section. Neutron stars are boundaries. They are limits. They are stable objects living close to a threshold, and that threshold is not a wall. It is the natural point where no stable configuration can exist, where gravity becomes too strong for matter's resistance, and beyond that threshold, a different state emerges. But tonight, we remain with the stable side, with the side where matter still holds on, where pressure still balances gravity, where a surface still exists, where light can still escape. Now let's make that feel calm, because limits in everyday life can feel restrictive. But in physics, limits are clarifying. They tell you what reality allows. They tell you what the universe is. Neutron stars tell us matter can be compressed to nuclear densities and still remain stable. Quantum rules can support star mass objects. The strong force can shape the stiffness of matter, Gravity can be intense without forming a horizon, and stability can exist very near the edge. So as you rest, let the final image be simple: a compact star, dense enough to bend space and time noticeably, supported by deep quantum rules, holding itself together, not forever, not beyond all possibility, but for unimaginably long spans of time, a stable survivor near the boundary, quietly existing, and in that existence, it teaches, it constrains, it reveals, not through drama, but through endurance, through the calm fact that it is still there. Take one more slow breath, and if your body is already heavy, let it be heavy. If your thoughts are already fading at the edges, let them fade, because we are not closing with an argument or a conclusion that demands precision. We are closing with a feeling built from real science, a feeling that the universe can hold extremes without losing its calm. Somewhere in the galaxy, a neutron star continues to exist, not as a moment, but as an object, a compact remnant, born long ago and still present. It does not need to do anything dramatic to be profound. It is profound simply because it is stable, because it is matter compressed to a boundary and still resisting, because it is gravity made strong enough to bend time and light and still not sealing itself behind a horizon, because it is an example of the universe approaching a limit without breaking. If you trace the story back, it began with an ordinary star, a long balance between outward pressure and inward pull, a patient negotiation maintained for millions of years, until fusion could no longer supply the needed support, and then matter was pressed and reorganized. Atoms gave way to denser forms, electrons could no longer remain in their familiar roles, protons and electrons combined, leaving neutrons behind, and the core became a compact object, held up not by heat but by quantum rules. This is one of the quietest miracles in physics, that stability can come from constraint, that pressure can come from the simple fact that identical particles cannot all occupy the same state, that matter can be supported even as the universe cools. Because the support is not thermal, it is structural, it is written into what particles are allowed to do. And then, layer by layer, the neutron star's interior forms a hidden landscape. A crust of heavy nuclei arranged in a lattice, a region where neutrons begin to move freely, a deeper core where matter becomes more uniform, a place where superfluidity and superconductivity may appear, and at the deepest levels, an uncertainty that is not frightening, only honest. Because the exact state of matter at the highest densities is still being learned. Perhaps it remains mostly neutrons, perhaps new particles appear, perhaps quarks become less confined. Whatever the details, the star exists, and the fact that it exists already tells us something about reality. It tells us that matter can be stiff. It tells us that pressure can rise fast enough to support a star's mass. It tells us that the strong nuclear force and quantum statistics can stand against gravity. Then there is gravity itself. Near a neutron star, space is curved strongly. Time passes more slowly at the surface than it does far away. Light loses energy as it climbs out, orbits behave differently, and yet the star remains visible. No event horizon forms. The universe is still open at that boundary. Light can still escape. Information can still travel outward. So neutron stars become a kind of bridge between ordinary astrophysics and the edge of black hole physics. They show us what strong gravity looks like when matter is still present. And then magnetism. In some neutron stars, magnetic fields become immense, not as a weapon, not as a threat, but as a configuration of energy threaded through space, so intense that it can stress the crust and reshape the magnetosphere, sometimes releasing energy as the star adjusts, not to frighten, only to settle, to move toward a lower energy state. Even magnetars, for all their extremity, are still expressions of law, electromagnetism in an unusual regime. Finally, the limits. A neutron star is not unlimited. There is a maximum mass beyond which no stable configuration exists, not because nature becomes chaotic, but because gravity eventually becomes too strong for any known pressure to resist. So neutron stars represent a boundary, the last stable form of star mass matter before horizons appear, and that boundary is one of the most calming ideas of all, because it tells us reality has structure, not only in the small, but in the immense. It has edges, not jagged or cruel, but defined, and those definitions come from the same rules everywhere. In that sense, a neutron star is a monument, not a monument built by intention, a monument formed by consistency. A reminder that the universe is capable of taking matter, compressing it beyond ordinary comprehension, and still holding it in a stable form, for millions, for billions, for spans of time so long that they feel like stillness. So if you are drifting now, you can let one final image remain, a small, dense star, turning slowly in the dark, its gravity shaping the space around it, its matter arranged by quantum rules, its interior layered and hidden, its surface still visible, its presence still communicating that the universe can be extreme and yet peaceful. And if sleep arrives now, it can arrive without effort, because nothing here needs to be solved tonight. The neutron star will keep holding itself together, the laws will keep balancing gravity and pressure, and your mind can do what the universe also does, in its own quiet way. It can settle, it can soften, it can rest,